Hello dear student, welcome to another lecture on quantum mechanics. This is my second lecture on quantum mechanics. Hope you have seen my first lecture. I encourage you to ask doubts in the comment section so that we can discuss more about quantum mechanics. In the previous video, we have learned about what is quantum mechanics, what is the difference between quantum mechanics and classical mechanics. We have discussed how the quantum mechanics evolved and what were the failures of classical mechanics which actually led to the discovery of quantum mechanics. And today in this video, we will learn about black body radiation. We will learn what a black body is, what is a black body radiation spectrum. We will look into the classical attempts which were made to understand black body radiation, and we'll see how these models, classical models, failed. And then we will see the quantum mechanical explanation for black body radiation, which is known as Planck's hypothesis because it was put forward by a famous scientist, Max Planck. Now, what is a black body? A black body is a perfect body which absorbs or emits radiations of all wavelengths. It is an ideal body. An ideal black body doesn't exist, but we can have many analogies for black bodies such as an electric heater, an incandescent lamp, our sun, our stars, etc. are perfect black bodies. It is a body which can absorb all radiation which falls on it irrespective of their wavelengths, and it is a body which can also emit all the absorbed radiation with all the wavelengths from 0 to infinity. So this is a body which appears to be black because it absorbs all the radiations which falls on it irrespective of whether they belong to the visible region or not. They absorb all the radiations, the infrared radiations, the ultraviolet radiations and the visible radiations which falls on it, which it will absorb as well as emit all the radiations, all kind of radiations which falls on it, and it can also emit all the wavelengths of light. Now, what is the speciality of a black body radiation? What is a black body radiation? When a black body is in uniform temperature, it will emit all the frequencies, and these frequencies will show a characteristic distribution depending upon the temperature of the black body. And this radiation is called black body radiation. I repeat, when a black body is in uniform temperature, it will emit radiations and their frequency distribution shows some characteristics. And this characteristics distribution is called black body radiation spectrum. What is black body radiation spectrum, and what are the importance or the features of the black body radiation spectrum? As I have already said, a black body radiation spectrum is a spectrum of frequencies which is emitted by black body. This was studied as the emissive power versus wavelength. That is, the power of an emitted wavelength is plotted against the wavelength, and we will get a spectrum, or we will get a plot which is known as black body radiation spectrum. The figure which is shown in this slide shows the black body radiation spectrum, or the black body radiation emissive power versus wavelength spectrum, or the plot is shown here. Emissive power, or the spectral radiance, is calculated as a power which is radiated per unit angle, per unit area, per wavelength. So it is a power of a single wavelength which is emitted through a certain angle in unit area. and this is plotted against the wavelength which emits this radiation. From the plot, it is evident that towards the lower frequencies towards the lower wavelengths, the increase in energy is proportional to the wavelengths. That is, when the wavelength increases, the energy radiance or the spectral radiance also increases, and it will reach a maxima which is at the visible region. Again, it comes down as towards the higher wavelength, the energy is decreased as the wavelength is increased. You can also see that the temperature, as the temperature rises, the energy, the spectral radiance also increases. The 3000 Kelvin line is very low while the 5000 Kelvin line is very high. It shows that as the temperature increases, the amount of energy released also increases. The plot also shows us that as the temperature increases, the peak point shifts towards the blue region, that is, towards a lower wavelength region. You all may already know that the wavelength and the frequency is inversely proportional to each other. That is, when the wavelength increases, the frequency decreases, or the wavelength decreases, the frequency increases. Here I say the peak is shifted towards the blue region. That means that the wavelength is decreased or the frequency is increased. When the temperature is higher, the peak of the wavelength or the peak of the spectrum shifts towards a lower wavelength region. There were many classical attempts which were made to describe what this plot actually says. This plot is an experimental data, so there were many classical attempts which were made to account for this behavior of black body or black body radiation spectrum. The first was from the scientist Wein, and this distribution he made on the basis of classical explanations. He made it on the basis of Maxwell's energy distribution. Maxwell's energy distribution is a classical energy distribution curve we use. And using Maxwell's energy distribution, Wein tried to explain the behavior of black body radiation spectrum. And the given equation is the black body radiation or the Wein's displacement energy, Wein's displacement equation, or known as Wein's approximation. It says that E lambda d lambda is equal to C1 lambda to the power -5 e raised to minus C2 by lambda t into d lambda. This says that E lambda d lambda, this is the energy between the wavelengths lambda and lambda plus d lambda. That is energy which is emitted by the wavelengths which has a wavelength between lambda and lambda plus d lambda. C1 and C2 here are constants. Lambda is the wavelength and T is the temperature. When this graph is plotted towards the lower wavelength, the energy distribution is almost like towards the lower wavelengths or the shorter wavelengths or the higher frequencies, energy distribution is almost like the black body radiation spectrum, because towards the lower wavelengths, the equation depends on the exponential term, that is lambda t term minus lambda t term, while towards the higher wavelength, as the lambda increases, the equation will depend more on the power of lambda raised to -5, and the distribution tends to deviate away from the behavior which is shown by the black body. So Wein's energy distribution spectrum was agreed only by the shorter wavelengths, that is higher frequency. Towards the blue region it was okay, but towards the red region it showed a higher deviation and it doesn't actually fit into the black body radiation spectrum. So Wein's energy distribution, even though was successful in explaining what the shorter wavelengths look like, but it failed to explain what the behavior of the longer wavelength region, that is the red region. Another attempt, which was also a classical attempt made by Rayleigh and Jeans, and this is known as Rayleigh-Jeans distribution, was also made to analyze the black body radiation spectrum. And the Rayleigh-Jeans equation E lambda d lambda is equal to 8 pi kt lambda raised to negative 4 d lambda, where lambda is the wavelength and E lambda d lambda is the energy emitted by the waves, which has a wavelength between lambda and d lambda. K is the Boltzmann's constant, and this curve was pretty good in explaining what happens towards the higher wavelength region, that is towards the red region, but it failed to explain as the wavelength decreases or as the frequency increases. It couldn't explain what happens towards the blue or the violet region. According to this equation, we know that lambda to the power negative 4, when it comes to the denominator, it is lambda to the power 4. So as the lambda increases, it will go into an ultraviolet catastrophe, that is when the energy or the wavelength increases, this distribution shows that the energy should reach a maximum or the infinity, which is not possible. So as the frequency increases or the lambda decreases, the energy goes to infinity, which we call as a ultraviolet catastrophe. So this distribution, Rayleigh-Jeans distribution, was successful in explaining what happened towards a higher wavelength, but failed to explain what happened towards the lower wavelength. The Rayleigh-Jeans distribution was based on the equipartition law of energy, that is, all the degrees of freedom will have the same energy. This is the equipartition law of energy. So it was based on the equipartition law of energy. This distribution assumed that the black body radiator cavity is full of wavelengths from 0 to infinity, and when these wavelengths reflected from the black body cavity, it formed standing waves, and this waves is being emitted. So their assumption was, first assumption was the black body radiator cavity was full of wavelengths from 0 to infinity, from the complete range of wavelengths, and these wavelengths are in the form of standing waves because they are being reflected from the walls of the cavity. And Rayleigh-Jeans distribution was also not much successful because it was not able to explain what happened towards the lower wavelength or the higher frequency region. Towards the blue region, it couldn't explain what happened towards the blue region, but it was a well good approximation towards the red region. Then came Planck, Max Planck. Max Planck came with his hypothesis based on quantum mechanics. Two classical attempts failed, so Max Planck first came with his first quantum explanation. Max Planck had some assumptions, and and the assumptions were: number one, the black body radiator chamber, the chamber of black body, is not filled with waves but is filled with harmonic oscillators. He assumed that there are many molecules which made up that black body chamber, and each of that molecules behaves as if they were harmonic oscillators. They were simple harmonic oscillators which has a definite frequency. As we have already studied about simple harmonic oscillators, that is a simple pendulum, for example, it will have a definite frequency. Every oscillator will have a definite frequency and it can only oscillate in that frequency. So what Planck hypothesized is that the black body chamber is filled with many molecules, and these molecules actually behaves as if they were harmonic oscillators of molecular dimensions. And since they were molecules, they had only 1 degree of freedom. That is his second assumption. And going to the third assumption, the Planck said that the black body radiator chamber which contains some oscillators, and these oscillators can vibrate only in specific frequencies. As I've already said, they can vibrate, they can oscillate only in specific frequencies. Therefore, they can radiate energy only in specific frequencies and not continuously. And this is a very, very important hypothesis, that he said the oscillator cannot radiate or absorb energy continuously. The radiation or the absorption of energy take place in discrete values and not continuously. This is the basis, very basis of quantum mechanics, where we say that the quantum world is discrete rather than being continuous. Everything we discuss in the quantum world, everything, even a field, energy, whatever physical properties a matter can possess, everything is quantized, everything is discrete and nothing is continuous. So Planck put in that hypothesis, put in the model of quantum mechanics here, and said that the oscillators or the molecules inside the black body chamber can radiate or absorb energy only in discrete values, and they cannot give out energy continuously. He also added that the energy exchange is in discrete quantity called quanta, and they are the integral multiples of a smaller energy unit. A smaller energy unit possessed by a smaller energy packet called quanta or a photon is h nu. The smaller energy which a photon can emit is h nu, and all these energies are emitted by photons. So the energies are integral multiples of photons. We have 2 photons energy, 3 photons energy. We can't have 3.5 photon or 3.5 photons. We can have only integral multiples of photon. Therefore, energy can only be emitted as integral multiples of energies of a photon. That is, E is equal to n times h nu, where n is only integers and cannot be half integers. N is equal to 0, 1, 2, 3, etc. and cannot be 0.5, 0.2, 0.5, etc. And the energy is emitted only as integral multiples of the smaller energy unit, and this is called quanta. The energy exchange can only happen through discrete energy packets called quanta, which has an energy E is equal to nh nu. Here h is a universal Planck's constant. This was a constant which was defined by the same scientist Max Planck, and the value of h is 6.6256 into 10 to the power negative 34 joule second. So, Planck hypothesis was based on quantum mechanics, while Wein's and Rayleigh-Jeans hypothesis was based on classical mechanics. Using classical mechanics, we failed to explain what happened, but using Planck's hypothesis, the model explanation for black body radiation was successful. Using Planck's hypothesis and considering that the energy is released only in the form of quanta which has an integral multiple energy of h nu, he derived this equation. Here you can see that the exponential power depends on the frequency, and also there is dependence on the wavelength, that is lambda to the power 5, and this radiating spectrum, this equation completely explained the black body radiation right from the lower wavelengths to the higher wavelengths. It also explained about the peaks. It also explained about the peak shifting towards the lower wavelength region, that is towards the blue region. It also explains why the spectral energy increases with temperature. So Planck's theory was very successful in explaining all the attributes of a black body radiation. The black body radiation was explained using quantum mechanics, using the Planck's constant H and the quantized energy values h nu. This inspired many other scientists to explain what happened, explained many other phenomena which were observed at that time. In 1905, Einstein used the same hypothesis to explain the photoelectric effect, and he gained a Nobel Prize for this explanation for photoelectric effect. In 1907, again Einstein used the same effect which was explained by Planck to explain specific heat of metals. In 1913, Bohr explained Bohr's spectral lines using this Planck's radiation. We have discussed about Bohr's model, and the failure of Bohr model was the Bohr was not able to account for the final spectral line splitting which happened in the presence of electric field and magnetic field, which we called as Zeeman effect. So Bohr was successfully able to explain using quantum mechanics about the spectral line splitting. Again, Crompton in 1922 used this same hypothesis to explain Crompton effect. Crompton effect is X-ray radiation. What happens when an X-ray hits a molecule, an X-ray hits an atom, and this effect was known as Crompton effect because it was observed by Crompton, and Crompton was able to explain this effect using the Planck's hypothesis. And this Planck's hypothesis was a very successful hypothesis, and it was able to explain black body radiation. Not only black body radiation, many other systems such as photoelectric effect, specific heat, the spectral lines, and the Crompton effect. So in this video we have learned about black body radiation and black body radiation spectrum. See you in the next video. Hope you are learning, and I encourage you to discuss your doubts with the comments. Thank you.